Hello, and welcome to this video that talks about sketching polynomial functions using our idea of end behavior as well as roots of the polynomial function. If you're watching this video, you should realize it assumes that you understand how end behavior works. This will show how to apply it in conjunction with our understanding of finding complex roots of a function, which are, in fact, the x-intercepts when those complex numbers are purely real. Okay, so let's read our directions here. It says, please determine the roots of the following functions. Also, use your knowledge of end behavior to create a sketch. The sketch should include all intercepts of the function, which means x's and y's. Okay, so we take a look at this example. I'm going to do two examples here. We see that the first one is y equals x to the fourth minus 5x squared plus 4. Okay, well, let's talk about the end behavior first. So I see that the degree equals 4, which more importantly is even. That's what you need to note. And I see that the lead coefficient is 1 for the degree term, and that is positive, so it's greater than 0. So I know that it's going to generally have this shape, which, as you see, the vocab for that is that as x approaches infinity, the output approaches infinity. As x approaches negative infinity, the output still approaches infinity. Okay, so we're going to keep that in mind when we make the drawing, and I'll try and do some color coding here. And I'll find the roots in blue. And the roots mean when the output is 0, synonymous with the x-intercepts, synonymous with the zeros of a function. Okay? Except if we get a complex root where it has an imaginary component, it really isn't the x-intercept, but it's still the root in that the output is 0 for that input. Okay, well, I'm actually going to factor this. It sort of looks like a quadratic trinomial, although it's 4th degree, but I can still use the same technique. So I'm going to go here and go 2 factors of x squared to start, and then say what are the factors of 4 that make negative 5? Well, that would be 1 and 4, as long as they're both negative. Now, using the zero product property, you'll see very quickly that this is just going to split into these 2 factors that I'll set equal to 0. And x squared equals 1 means x is equal to plus or minus 1. That happens by square rooting both sides. Don't forget the plus minus. And similarly here, x squared is equal to 4 means x equals plus or minus 2. Similarly, again, by square rooting both sides. And don't forget the plus minus. So I actually have 4 x-intercepts here, and I'll label them. We've got 1, 2, negative 1, and negative 2, right? And then on green, I'll do the y-intercept, which is very simple here. It just means that x equals 0. So I'll do f at 0 for the function, which means plug the function's input to be 0. And that's going to give me 0 to the 4th minus 5 times 0 squared plus 4, which is this equal to 4. Okay, it's just the constant term on the end. Just showing a little bit of writing here to sort of respect the process. So now I've got a y-intercept of 4. So back to our end behaviors, which I'll go in red. We see here that we need to make sure as we approach infinity by way of the input, that the output approaches infinity. So it looks like this. Similarly, as x approaches negative infinity, the range also will approach infinity. And then the part in the middle that I sort of have to guess at a little bit, and that's why I put a dotted line, will look like this. Okay, without a graphing calculator doing derivatives, I can't exactly verify those points. Now keep in mind, although this is blue, I'm just using the magic pen. I don't know if it comes all the way down here, or if it's more shallow, or if it's more concave or convex. What I'm trying to say by writing those dotted lines is I really don't exactly know what points it's going through, but I'm generally thinking that the shape is going to be like that. Okay, but the end behaviors, I can guarantee they definitely tend to look like they do. Okay, so I'll do another example here. I'll do something of the cubic nature. Okay, so let's take a look at this one here where it says number 3, y equals negative x cubed minus 2x squared plus 35x. I notice that the degree is equal to 3, which is odd. Okay, and then I notice that a is equal to negative 1, which is less than 0. So that means that my general shape will look like this of the function. Okay, and that says as x approaches infinity, y approaches negative infinity, and as x approaches negative infinity, y approaches positive infinity, which means when you go to the right, the function goes down. If you go to the left, the function goes up, all that good stuff. Okay, so I'll find my roots here by setting the function equal to 0 and finding the values for x. If we notice here, I'm going to factor out a negative x to start, get negative x, which then gives me x squared minus 2x, plus 2x minus 35, understanding that you have these sign changes because you factored out the negative, right? Okay, and now I'm going to factor again because I actually noticed that there are factors in negative 35 that will make 2. So I'll make 2 linear factors here. And I think that 5 and 7 would fit nicely as long as the 7 is positive and the 5 is negative. And then I'll use a zero product property for all this. The factors probably jump out at you pretty quickly as x equals 0, x equals 5, and x equals negative 7. So I'll put those on my graph. X equals 0 and x equals 5. The y-intercept I've sort of found here incidentally. It's when x equals 0. So plugging that in, you'll still notice that you're getting 0 because when one of the x-intercepts is the origin, it's also the y-intercept. I'm plugging 0 into the original function because there's no constant term. You should see that pattern by now. Okay, I'll put a little green dot there, just so you know that the x-intercept is the same as the y-intercept there at the origin. Now I'm going to go back to my idea of my end behavior and say that when x approaches infinity, which is going well past 5, y approaches negative infinity. Similarly, as x approaches negative infinity, y is going to approach infinity. And then here, just sort of making a general guess, that's why I use a dotted line. You could go to your graphing calculator and verify a more exact type of function in terms of the graph you draw. Again, if I wanted to talk about these relative maxes and mins, I would find the derivative and set that equal to 0. It's not what's being asked here. You just asked for a general sketch using end behavior and finding the roots. Okay? Neither of these examples had finding complex roots. If you found complex roots, you just list them in the roots, but you wouldn't be able to graph them because the fact they're complex in that they would have an imaginary part means you can't really put them on the number line. Okay, so enjoy and practice, and I hope that helps.